Okay, okay, okay. Am I okay? I was not visible in that. So okay, okay. Thank you, thank you. So but still again. Okay. Okay. Now it will be so. Okay. So let us start with the first question. So first question is consider feedback system shown in figure. So there is a feedback system. Determine the frequency at which the circuit will oscillate and assume A beta equal to 1. Let beta of s equal to 1 by s plus 1 say 4 zeros, right? So 1 0 0 0 0 whole power 4. So this is beta of s. So the question is to determine the frequency at which the circuit will oscillate. Okay, so this is the circuit. So as we can see here, okay, so as we can see here, this feedback circuit, and the given that the assumption is that like A beta is equal to 1, right? So okay, where is not okay, so the assumption is okay, I don't know, let me check the input. Okay, oh, okay, okay, now it took, okay. Okay, so other assumption is A beta equal to 1. Okay, and there is a system given here. So this is actually the forward path, right? Open loop path, and say the gain is A. Okay, and the output is given to a feedback module which has a gain beta. Okay, and this depend upon the frequency, right? Beta of s, and this again given back to the this amplifier. Okay, so the question is like find what is the frequency of oscillation. So we know according to Barkhausen criterion it should satisfy, the circuit should satisfy two conditions, right? One is like the gain, the loop gain must be equal to 1, and the second is like the loop, the entire angle due to this loop must be a multiple of say 360. So where n is equal to 0, 1, 2, etc. So that is like if there is some signal here, when it travels through this amplifier with gain A and through this beta feedback, and at last it will reach this end, right? So if the phase is theta, the whatever the angle come here, it will be theta plus n 360. So that is like both the signal must be in phase, then only there will be positive feedback, right? So then only we will get a signal, an oscillating signal. So that is a condition here. So if we check the circuit, here, the forward amplifier is a negative is an inverting amplifier, right? So this is actually an inverting amplifier. So here it is V in and this V out. So what the signal, if this is in phase, if there is a sinusoid here, this will be 180-degree phase shifted signal. So what is the phase difference here? It is 180 plus or minus 180, right? Okay, so for satisfying the Barkhausen criterion, if there is some signal here, it should also be again 180-degree phase shifted at this input. So in order to make this circuit to be oscillating, we must have this beta, the angle due to this beta of s must be 180-degree. So we just need to find what is the frequency at which this produces this 180-degree phase shift. So how to find? We just need to find what is angle of beta of s. Okay, that is angle of beta of j omega. So we have this beta of is here given. So 1 by s is j omega plus say 10 power 4, right? 10 power 4 power 4. Okay, so what is the angle here? So angle is minus tan inverse omega by 10 power 4. Okay, so there are 4 terms here, right? 4, so this into 4. This is angle. This is the angle. So this is equal to, this must be equal to 180 plus or minus 180. So we will assume it to be minus 180, or we can take the other way. So then only we will get total 360 degree, right? So how we'll find omega? Just calculation. So 180 by 4, this will be 45. Okay, so omega by 10 power 4 will be equal to tan 45. So omega equal to tan power 4 into tan 45 is 1. So omega equal to 10 power 4. Okay, or the frequency of oscillation is 10 power 4 by 2 pi. So whatever is the value, that is a frequency. So this is how we will find determine the frequency of this circuit. Okay, so I guess it's clear. Yeah. Ha. Correct. Like we will just assume this this block as like this, right? See, there is some forward amplifier A, and there is some feedback amplifier B, beta. Okay. Sorry. Okay. So the output of A is given to beta. So what is here? What is the amplifier? So this is some amplifier, right? So what is the amplifier taken here? It is, again, it is actually feedback amplifier. It is an inverting amplifier here. Inverting configuration. So what is the gain of this this amplifier? This is R2 minus R2 by R1. Okay, so it is like if I give some signal here, it is 180-degree phase shift. So we just take that like 180-degree phase shifted signal. Correct. So an example I will show you for I will show you. So actually sir has explained about vein bridge, right? So there is another circuit, like I will show another circuit, like okay. So yeah, reason is that like already in the forward path there is one 180-degree phase shifts. So right, so like either there is some signal. Correct. Entirely 360. Okay, so this one circuit, though it is not accurate to the RC phase shift, but we can assume like this is somewhat same circuit. So here this is the feedback. This is the feedback path. Okay, so there is 3 RC. Yeah, that is different. This oscillator is known as RC phase shift oscillator. Okay, and the circuit that sir taught is like vein bridge. So there I will show that. Okay. Correct. That's it. So okay. Anyway, I'll explain since Banerjee has asked one question, right? So this is the circuit that sir has drawn, right? I guess it is similar. So see here this is the amplifier. So this amplifier, what is the phase shift due to this? So input to this is through feedback of this, right? So what is a phase shift created by this? Phase shift is 0. Phase shift is 0, right? So whatever is signal coming here, the same will be. So non-inverting amplifier. So what must be the phase shift created by this feedback circuit? This must be 360 or 0, 360 or multiple of 360. That's it. That's why during the derivation, sir would have mentioned about that. Okay. Similarly, if this is the configuration, if yeah, please. So if this is the configuration, this circuit is known as RC phase shift oscillator. Okay, so this is actually forward path gain, so A. So this has a 180-degree phase shift, and this is given to an RC phase shift like RC feedback circuit. Okay, so there are 3 RC feedback circuit. So if I give input here, so like already here 180-degree phase shift is there. Okay, so when this signal is given to this, the output of this at this point it will be 180-degree phase shifted signal. Means for a particular frequency omega, say omega naught, the frequency will be, the phase will be here 180-degree phase shift with respect to this input here. Okay, so net it will be 360. So that's how this RC phase shift oscillator works. So this question given here is somewhat similar to that. Okay. Okay. Input means actually the which input you mentioned? Input means output of this amplifier, right? This, right? This is output of this amplifier. It is given to, this is the input here, and the output is taken, this output of this feedback is from here, this here to this. This is the output given. Yeah. Okay. Yeah, only for a particular frequency the Barkhausen criterion will be satisfied. That's why only we are getting only one signal, right? Signal with only one frequency, right? Only at that frequency it is acting as a like positive feedback, and we will get and satisfy the Barkhausen criterion, and we will get a sustained oscillation. Okay. Correct. Same is applied here. So frequency of oscillation depends upon at what frequency. Here RC combination, like in this case, at what frequency the signal gets 180-degree phase shifted to here, to its output, in this case, right? Or we can say like at what frequency the entire loop gains, like A beta, angle of A beta is 360 or 0 to whatever, like multiple of 360. Okay. Both are same. Means only at this frequency there is sustained signal, right? Only this signal is being added up. So like for example, I will draw here, like if so A beta. Okay, so like if there is one signal, that has to be added up, right? So we should get a signal which is of same phase, then only it will get added up and will get a signal that only will be sustained, like that signal only will be sustained. Okay. So there are other circuits also, like instead of this, like if I have an amplifier here, there are also tank circuits used with inductors and capacitors. Okay, so like this is one configuration, another is such a configuration in feedback. So at particular frequency, this feedback will feedback plus the phase of this A. Okay, means forward path, it will lead to 360-degree phase shift. So these are high frequency oscillators. Means in high frequency oscillators we use inductive and capacitive inductor and capacitors as tank circuit, and that will lead to such frequency. So these are known as like this is known as Hartley oscillator, and this is known as Colpit oscillator. It depends upon which format we used, whether 2 inductors and capacitor and 2 capacitor inductor in feedback. So there are such oscillators also there. Okay, so there are, like in general we can say, like we have RC phase shift oscillator, Wien bridge oscillator, okay, Hartley and Colpitt oscillator, Hartley and Colpitt oscillators. Okay, there are many multi-vibrators that sir has discussed. A crystal oscillator is so like that, but crystal oscillator is like we have one crystal like piezo crystal, and the excitation is different. That's it. So these are various oscillators. In each of this, the gain, the forward gain may be like the forward gain may have produced some phase shift like 180 degree in Wayne bridge, see, as we saw, and in RC phase shift means in Wayne bridge it is 0, right, and in RC phase shift it was 180. Okay, similarly it will be varying in Colpitt and Hartley. So whatever is the configuration, the end thing is like it has to satisfy the Barkhausen criterion. So whatever the feedback we have taken, we just need to check at what frequency the entire gain, means entire angle A beta is a multiple of 360. So that at that frequency only it will oscillate. Okay, so let us check the solution. So this is the solution for this, as we have discussed. Here 180 degree phase shift is there, so we have to, now to satisfy the Barkhausen criterion, we just need to find what is the frequency at which the feedback angle is minus 180. So that's so we have substituted here, and we got the frequency to be 1.59 kilohertz. Okay, so whatever we have discussed, the same thing. So let us go to the next question. So I guess it's clear. So second question is, for a Wayne bridge oscillator shown in the figure, determine the resistance value R such that the frequency of output sinusoid is 10 kilohertz. Assume C equal to 0.01 microfarad. So this same Wayne bridge oscillator, and given the C value, C is given as 0.01 microfarad, we need to find what is the value of R. So it is pretty much straightforward. We know already what is the frequency of oscillation for a Wayne bridge oscillator, that is omega naught equal to 1 by RC. Okay, and given is its frequency 10 kilohertz, right? So R will be equal to 1 by omega naught C. So what is omega naught? 2 pi into the frequency of oscillation. So 2 pi into 10k, and capacitance value is 0.01 microfarad. So we just need to substitute for the frequency. So we already know for standard Wayne bridge oscillator it is 1 by RC. Just need to substitute that, and we will get the resistance R. So that's the question here. Okay, so let me check. Okay, so that is the solution given here. So R equal to 1 by 2 pi FC, and on substituting we will get the same frequency 1.59, not frequency, resistance 1.591 ohm. Okay, so that's it about this question. Coming to the third question. So okay, so both are same. Like third question is, for the Wayne bridge oscillator shown in figure, determine the resistance value R2 such that the frequency of output sinusoid is 10 kilohertz. So same question, given C equal to 0.01 microfarad and R1 equal to 2.2 kilo ohm. The question is just to find what is the value of R2 here. So already we have designed what is the capacitance value. Already given capacitance value, we have designed for resistance R for a particular frequency. Also, in order to work as a Wayne bridge oscillator, the gain must be A beta equal to 1, right? So A beta must be equal to 1. So based on this, we can decide what is the gain. Not this gain is like what is the gain of this circuit, this forward path. So what is the gain of this forward path? So we know for a Wayne bridge oscillator, to have a sustained oscillation, the gain A must be equal to 3, right? So you have gone through the lecture, and there you have gone through the derivation or design of this Wayne bridge oscillator. So you have seen like the forward gain of the Wayne bridge oscillator must be equal to 3. Okay, so we know what is the gain here. So this is actually a non-inverting amplifier, right? So what is the gain here? It is 1 plus R2 by R1. So that is equal to 3, which means R2 by R1 equal to 2. The question is to find R2. So R2 is equal to 2 into R1. So what is the R1 value? 2.2. So the value will be 4.4 kilo ohm. Okay. So again, we just need to know what is the frequency of oscillation and what must be for to satisfy the criteria, what must be the gain. That's it. Okay. Okay. So we'll check the solution. Okay, so gain A equal to 3, so we substituted the value of R1 and we got R2 equal to 4.4 kilo. Okay, so that's all about the third question. Fourth question, determine the maximum and minimum frequency of oscillation of a Wien bridge oscillator circuit having a resistor of 30 kilo ohm and a variable capacitor of 100 picofarad to 10 nanofarad. So in the previous question, the resistance is fixed while the capacitance, this capacitance is varied. Both the capacitance is varied from 100 pico to some tens of nanofarad, right? Okay, so we just need to find what is the frequency sweep of that. So what is the frequency? F is equal to 1 by 2 pi RC. So already the resistance value is given as 30k. Okay, and the capacitance will vary. So one frequency will be maximum frequency and one will be the minimum. So what will be the maximum frequency? Maximum frequency means the frequency at when the capacitance is least, right? So 100 pico is the least here. So 2 pi into 30k into 100 pico. And what is the minimum frequency? When the capacitance is maximum. So 2 pi into 30k into 10 nano. So this is the frequency, maximum minimum frequency. So that if we have a variable capacitor, we just need to vary, like given the variable capacitor is 100 pico to 10 nano, so we can get the frequency of oscillation in between this. Okay. Okay, so that's given here. Solution. So F max equal to 1 by 2 pi 30k into 100 pico. So we got the result as 53.05 kilohertz, and F minimum is when capacitance is 10 nano, so we'll get 530.5 hertz. So we can vary from 530 to 53 kilohertz. We'll have an oscillator which frequency can vary from 530 to 53 kilohertz. Okay. Okay. Now coming to the fifth question. For a bistable multivibrator shown in figure, determine the upper and lower threshold voltage. So we have been given with a multivibrator. So given R1 equal to 5, R2 equal to 10k, and saturation voltage VL plus as 10 volt and VL minus as minus 10. Okay, so so this is a bistable multivibrator, right? So the output will be either in one of the stable state, either it will be in the saturation voltage plus 10 or it will be in minus 10. Okay, but at what voltage of input? Okay, at what voltage of input the output changes from plus 10 to minus 10. Okay, or minus 10 to plus 10, that we have to find. Okay, how we will find? We just need to check what is the voltage at this point. So we'll call this point as VA. So what is the voltage here at VA? Since it's a potential divider here and there is no current, say we assume this to be ideal, right? So 0 ampere current. So what is the voltage VA? VA will be equal to V0 into R1 by R1 plus R2. Okay, so we have one input signal. Say we have input signal given here, and whenever this input voltage Vin is less than VA, when Vin is less than VA, what will be the output? Output will be minus. Okay, it will be minus Vset. And when Vin is greater than VA, it will be plus Vset. Okay, so at each of this voltage V0, the VA will change, right? So for example, if V0 equal to say minus Vset, okay, so what will be VA? VA will be equal to minus Vsat into R1 by R1 plus R2. So we will substitute R1 and R2. R1 is 5, right? So 5 by 5k, 5 by 5 plus 10. So 5 by 15, so it is 1 by 3. So Vsat minus Vsat by 3. Okay, it will be near to, like Vsat is 10, so it will be near to 3.3, right? Minus 3.3 volt. Okay. Minus 3.3 volt. Okay, and when V0 equal to plus Vsat, what will be the VA? VA will be equal to plus Vsat into, again, R1 by R2, R1 by R1 plus R2 is 1 by 3, right? So it will be equal to 3.3 plus 3.3 volt. Okay, so what happens is, like whenever the input, okay, whenever that input crosses 3.3 volt, whenever the input crosses 3.3 volt, the output will be minus. So it will goes to minus Vset. So till that it is plus Vset. Okay. Again, now the VA is minus 3.3, right? So whenever the input crosses this minus 3.3, so when the input reduces more than 3.3, then it will again, the output again goes to plus Vset. Okay, so it at these values it is stable, right? Till the input crosses a particular voltage, the output is stable, and when the input crosses these two limits or these two threshold values, it will change. So these two values, that is minus Vsat by 3, okay, and plus Vsat by 3, these are the threshold values. So which is the value, higher value, that is plus Vsat by 3, this is upper threshold voltage, okay, and which is lower threshold voltage is minus Vsat by 3, that's it. Okay, so 3.3 and minus 3.3, these are the upper and lower threshold voltage of this bistable multivibrator. Okay, so that is the question. So let me show you the solution. So it's clear, like we just need to find the threshold voltage. So that is the voltage seen here when the voltage V0 is at VL plus, that is VL plus into R1 by R1 plus R2, so we will get 3.33 volt, and lower threshold voltage is when the V0 is VL minus, so we will just substitute that here, so we will get minus 3.3 volt. Okay. Okay, now coming to the sixth question. For the bistable multivibrator shown in figure, determine the upper and lower threshold voltage. Okay, so again it's a bistable multivibrator. Given R1 equal to 5K, R2 equal to 10K, and saturation voltage VL equal to 10 and VL minus 10. So all the inputs are same, or parameters of or the component values are same, but the only difference is like the input given is at the non-inverting terminal, like the components to the input of the non-inverting terminal. So inverting terminal is grounded. Okay, so again to determine the upper and lower threshold voltage, we need to find what is the voltage here. So again VA, we will assume it to be VA. So what is VA here? So VA equal to, so now the VA is dependent upon both Vin and V0, right? So due to Vin, what is the VA? Vin into the voltage across R2, right? So Vin into R2 by R1 plus R2 plus voltage due to V0, so V0 into across R1, right? So R1 by R1 plus R2. So this is the voltage VA. Okay, so whenever the Vin the only V0 will be depending upon the voltage difference between the inverting and non-inverting terminal, right? So like whenever the VA here, so since the inverting terminal it is grounded, so it will be 0 volt, right? So whenever VA is greater than 0 volt, the output will be plus Vsat, and whenever the VA is less than 0 volt, it will be minus Vsat, right? So we just need to find for which values of Vin, for example, if V0 is Vsat plus Vsat, for what value of Vin this point VA crosses 0. So what we will do is, like, we will find at VA equal to 0, what is the relation between Vin and V0. Okay, so applying this, it will be 0 equal to Vin R2 by R1 plus R2 plus V0 into R1 by R1 plus R2. So it will cancel off. So what is Vin? Vin will be equal to minus V0, so R1 by R2. So this is the input voltage at which the VA is equal to 0. Okay, so this is the input voltage Vin at which the VA will be equal to 0. So there are two conditions, right? So when V0 equal to plus Vsat, so what will the Vin, what must be the Vin, so that VA will be equal to 0 or crosses 0. So we'll substitute that here. So Vin equal to, okay, minus of V0 is plus Vsat, so Vsat into R1 by R2. So at this value, so Vsat, so this is Vsat is 10, right? So minus 10 into R1 is 5 and R2 is 10k. Okay, so it is equal to minus 5 volt. So at minus 5 volt it will cross 0, right, when V0 is plus Vsat, and similarly when V0 is minus Vsat, Vin is minus of minus Vsat into R1 by R2. So this is plus 10, right? Minus plus 10, so into 5 by 10. So it is plus 5 volt. Okay, so which means, like, for example, if V0 is plus Vsat, okay, Vin must cross the voltage minus 5. So when Vin crosses minus 5, the output will change to minus Vsat, and after that again now it will be minus Vsat. Now Vin must cross plus 5 volt, so that again the output will change to plus Vsat. Okay, so these are the two threshold voltage, and which is the lower one, this is the lower one. So this is the lower threshold voltage, and this is the upper threshold voltage. Okay, so I'll show the solution. Okay, see, so we'll find what is the voltage. So here we have assumed it as V1. V1 is V into R2 by R1 plus R2 plus V0 into R1 by R1 plus R2. We'll substitute V1 to be 0, so that is the voltage at which it crosses the 0, right? So we'll find Vin for that. So Vin equal to minus V0 into R1 by R2, and we'll find what is upper threshold voltage and lower threshold voltage. Okay, so it is 5 and minus 5. Okay, now coming to 7th question. Okay, for 7th question, for the bistable multivibrator shown in figure, determine the upper and lower threshold voltage. Okay, same question, I guess. Yeah, so given R1 equal to 5k, R2 equal to 15k, and the saturation voltage is VL plus equal to 5 and VL minus as minus 5. Also draw the hysteresis. Okay, so here given it is again the input is at inverting terminal, while a DC voltage is being provided or inserted at the non-inverting terminal, right? So there is one DC voltage, that is the only difference between the this and the previous one. Okay, the question is, like, if I insert a DC voltage like this as 2 volt here, so what will the change in the upper and lower threshold voltage? Okay, so we'll see, we'll find how to find what will be the value. So again, how we'll find? We'll just find by finding what is the calculating what is the voltage here, say VA. So what is the voltage VA here? So when, like, for example, if I are not given input Vin, and we'll find what is the voltage VA due to the voltage 2 volt and V0. Okay, so due to 2 volt it is VA equal to 2 into R2 by R1 plus R2, that is by superposition, and plus due to V0 is V0 into R1 by R1 plus R2. Okay, so this is the VA voltage. Okay, so what is R1 and R2 value given here? So 2 into R2 is 15 by R1 plus R2 is 5 plus 15 plus V0 is V0 into R1 is 5 by 5 plus 15. So everything is K, so that will cancel off. So we'll get 2 into 15 by 20, right? So I can write it as like so 5 by 20 is like, so 3 by 4, right? 15 by 20 is 3 by 4 plus V0 into, so 5 by 20, so 1 by 4. So it is like 6 plus V0 into 1 by 4. So this is the VA voltage. Okay, so we have again two cases, like when V0 is plus Vsat. So when V0 is plus Vsat, what will be VA? V will be equal to 6 plus Vsat by 4. Okay, so Vsat is plus 5, so 6 plus 5, 11 by 4. Okay, and when V0 is equal to minus Vsat, that is VA equal to 6 minus 5 by 4, it is 1 by 4, right? 1 by 4. Okay, so these are the two voltage. This is the upper threshold voltage, and this is the lower threshold voltage. Okay, so these are the two voltage at which the output will vary. So as you can see here, what's the difference when I connect a 2 volt here? Both the upper threshold and lower threshold voltage is positive. See, this is plus 11 by 4 and this is plus 1 by 4. Okay, so I will just draw the hysteresis. So I have UTH, right, as 11 by 4 and lower threshold as 1 by 4. Okay, okay, so upper threshold is 11 by 4, so I'll write it here, 11 by 4 and 1 by 4. Okay, so assume the output is high. Okay, output is high means the threshold is 11 by 4. Okay, so till that V0 will be high, right? So till that V0 will be high, say V sat. So when the Vin increases gradually from 0, it will increases till 11 by 4. After 11 by 4, the output will suddenly vary to minus V sat. Okay, so minus V sat. So above that, the output voltage will be minus V sat. Okay, so it will cross like this. And now what, when now it is like output is minus V sat, what will threshold voltage now? Lower threshold voltage is this one, right, 1 by 4. So when the input voltage again come back or reduces back to 1 by 4 voltage or crosses the 1 by 4 voltage, okay, or the input goes below 1 by 4 voltage, what happens? Again the output will change to V sat. Okay, like this. Okay, and for all the lower voltage lower than this, the output will be V sat. Okay, again on increasing, it will follow this path. So this is the hysteresis. This is the hysteresis for this bistable multivibrator. Okay, so I guess that's it clear. Okay, so I will show the solution. Okay, so this is the solution. So again we assume this as V1 and we found what is the V1 in terms of this DC volt, 2 volt and V0. So this is the value. We substituted for both upper and lower threshold voltage, VL plus and VL minus, and we got two values, that is 2.75 volt and 0.25 volt. 11 by 4, right? So 11 by 4 and 1 by 4. Okay, and this is the hysteresis that we just discussed now. Okay, I guess it's clear. Okay, the only thing is like we just need to find what is the voltage at this node. That's it. Okay. Okay. Now coming to the next question. For a stable multivibrator shown in the figure, determine the frequency of square wave if the values of component used are C1 equal to 0.1 microfarad, R1 equal to 10 kilo ohm, R2 equal to 100 kilo ohm, R3 10 kilo ohm, and L plus and L minus is 10 volt. Okay, so it's basically a stable multivibrator. So we know the output will be a square wave, right? It will be a square wave, and there will be two. This is on time and this is the off time. Okay, so what is on time, or like instead of T1 and T off, we'll say like T1 and T2. Okay, so what is the total time? What is the total period? T is equal to T1 plus T2. So we just need to find this T, right? This is repeating, so we will get the frequency of oscillation as F equal to 1 by T. Okay, so we know what is the time period T1 and T2. Both time T1 and T2 are equal, right, here. So T1 and T2 will be equal to RC natural log, so 1 plus beta by 1 minus beta. So this is the time period of an unstable multivibrator realized by an op amp. So what is beta here? Beta is equal to, so beta is this ratio, right? So beta equal to R1 by R1 plus R2. Okay, so this is beta. So if I just calculate, so already given R1 and R2 value, right? R1 is 10k by 10k plus 100k. So I know this value, I will get a value here, 10 by 110. Okay, so I can substitute here this value, Similarly, this RC means this resistance, this feedback resistance is the R. So we can write this as R3C. Okay, so already R3 has been given, 10K is given, the capacitance C is given as 0.1 microfarad. So I can find what is T1 and T2. Since T1 and T2 are same, so T1 equal to T2. So time period T equal to 2 into R3C natural log 1 plus beta by 1 minus beta. So you can calculate that. So 1 by T will be the frequency. Okay, so okay, beta means like beta is a feedback factor here, right? So simple, like we just need to, the thing is like we just need to understand the working, that's it. So here when we see, okay, so suppose say initially V0 is some high voltage, say V plus value. So what will the voltage here? So it will be V plus into R1 by R1 plus R2. Okay, so it is high. So what happens is, like, since this is V plus and initially we will assume that there is no the capacitance is not attain the voltage V plus, means it will charge like this, right? So it will charge like this. So VC will start charging and it will charge to this V plus. So it starts from some, we don't know, it will start from some value, and at a particular voltage it is actually trying to charge to V plus. But the thing is, like, here the voltage is V plus into R1 by R1 plus R2. So when this VC crosses this, when this voltage, suddenly this voltage, the voltage at minus or inverting terminal will be greater than this plus. So suddenly this will be V minus. So at that voltage, like, so at a particular voltage here, at that voltage the output will suddenly change to minus, V minus. So here this will be R1 into V minus by R1 plus R2. So again the capacitor will now charge like this, like this is minus, right? So the current will flow in this direction, and it will discharge till the voltage reaches this voltage. So these are the two peaks to which the capacitor charges, like like R1 into V plus by R1 plus R2, and here R1 into V minus by R1 plus R2. So this ratio is known as the beta. So beta V plus and beta V minus. Okay, so if we know the working, means already we know, like, what is the this voltage here. So R1 by R1 plus R2. So this is the beta value. Okay, so already in the question itself it's not given what is beta, but we have to assume. Why? Okay, but like which node? See, I'll show, like, which node is actually varying. So this is constant for a value, right? So beta into Vsat or minus Vsat is a constant for a particular time, right? While the only changing voltage is here. Correct? Okay, so that's why, like, even here also this voltage is changing due to V0. Here also it should have changed if there is some capacitor or inductor here, but it is actually fixed. R1 and R2 is a fixed value, it doesn't depend upon the frequency. So this voltage is fixed. Okay, so with respect to this we are going to say how this capacitance voltage is changing. So this capacitance actually it should have been Vset directly, right? If this is fixed, this also into V0 into some resistance. If it was a resistance, it will be V0 into R3 by R4 by R4 plus R3. But it is actually a capacitor, so capacitor won't change suddenly. The voltage across the capacitance won't change suddenly. So it actually slowly it will change. So that's why we are finding, okay, so let it be at which node the voltage is constant, we will see. So at this node only the voltage is constant. And what is that voltage? Beta into Vset. Okay, constant when the capacitor is varying. Okay, so that's why we are assuming that to be we are taking this this as the ratio, and also we are just denoting that value r1 by r1 plus r2 as beta. That's it. I can even write it as some alpha. It doesn't matter. It's just a notation. Huh. Okay, fine. So like in our RC phase shift oscillator, Wien bridge oscillator, now it is like that, right? So feedback is varying. Yeah, correct only. So that time this configuration is different. Why? No, nothing like that. Like, what is the feedback here? Both are feedback here, but the thing is like the variation here is different, right? See, this is constant, but this is varying very slowly. Okay, and here as such, like the positive feedback is more here. It depends. Like that day we I think in last class we discussed, right? For a particular constant value, it is fixed. Like only at this area it changes. That's why. So that's why, like, if this is actually constant value, this voltage is not up to this value, so it will slowly change. The voltage will slowly change. Like here, don't confuse with the Barkhausen criterion or the oscillators which we discussed earlier. Don't confuse with that. Okay, it is just like how the output, like the stable output, is changed with respect to time. That's it. So that is being exploited here. That's why it is like known as multi vibrators. Like, don't confuse with the don't confuse. Like the thing is like don't confuse with the like the oscillators which was discussed earlier. That is with respect to Barkhausen criterion here. This is a oscillating circuit where the output is changed from means like they are exploiting in changing the stable output voltage from one stable point to another. That's it. Like you would have gone through the lecture. So we have three different monostable multivariator, bistable multivariator, and astable. So whether the output is stable in steady state, that is what we are going to attain here. So here what happens is like the capacitance like at a particular state, when if you assume like at a particular state it is stable, say Vsat at plus Vsat, it is not stable. Like the capacitor goes on charging slowly, and at a particular point this voltage will be greater than this voltage, so the output will suddenly jump to minus Vsat. Okay, so it is actually exploiting this this sort, like we have so previously we saw the bistable multivariator, right? So it is stable at both the state is stable. So the same is actually exploited here, but the thing is like input is varying. The input here, instead of giving an input here, we are just assigning a capacitor here, and this is dependent upon the output voltage. Okay, so when we connect a voltage here, it will definitely, the capacitor will charge, right? Capacitor will charge to a particular point, and this voltage is compared with this node. That's it. Correct. Yes. Okay, so that's it. So we have been given all the values, R1, R2, R3 and capacitance value. So we already know what is the time period of the oscillation. We just need to find what is the beta value. Just substitute that and we'll get what is the time period. That is 45.6 microsecond. And just the 1 by t will be the frequency, right? So f equal to 1 by t, you will get 21.9 kilohertz. So that is the frequency of oscillation of this astable multivibrator. Okay, now coming to the next question. that is for a again it's an unstable multi-orbit. So for an unstable multi-orbiter shown in the figure, determine the on time and off time of the output square wave. If the values of the components are used are C equal to 220 nanofarad, R equal to 10 kilo, and L plus and L minus is means minus L minus is 10 volt. Assume both the diodes to have 0 on resistance and infinite off resistance. That is like assume the diode to be ideal. That's it. Okay. So given this circuit, so again it is similar to a stable multi-orbiter, but the thing is like in the feedback we have been connected with two resistors, 2K and 1K, and that is through two diodes, D1 and D2. So what happens, like for example, if the output V0 is high, like if the voltage is high, say Vsat, what happens is like this voltage will be plus with respect to ground, right? So the voltage is plus Vsat, so diode D1 will be on, right, and diode D2 will be off. So in effect there is only this and the resistance on resistance of this diode is 0, right? So in effect during when it is plus Vsat, this in feedback the resistance will be 1 kilo. Okay, similarly when the output is minus Vsat, diode D1 will be off and D2 will be on, right? So in effect this will be short. Okay, so and this will be off, right? So in feedback it will be 2K. So the only thing is like, so during the on time, okay, during the on time or the when the square pulse is positive, okay, the value of the positive pulse amplitude is positive Vsat, the time period T1 depends on the resistance 1K and C, and similarly when it is off, say T2 will depend upon the capacitor C and 2K. Okay, so that's it. So we can say like when V0 equal to plus Vsat, okay, D1 is on, right? D1 is on and D2 is off. So like okay, so this is T1, so we'll call this as on time and this will call it as off time. So it is T1 and T2, that's it. So what is on time then? Now again we know it is like RC. So what is the value of this R3C? R3 is now D1 is on, right? So only this path. So R3C natural log 1 plus beta by 1 minus beta. So again here beta, what is beta here? It is R by R plus R. So it is 1 by 2, right? So 0.5. Okay. So what is R3 here? R3 now here is 1K. So 1K into 220 nano into natural log of 1 plus 0.5 by 1 minus 0.5. Okay, just calculate, we will get a value here. Again, what is T off? T off is like same, but the resistor diode D2 is on, right? So the R3 will be 2K. So 2K into 220 nano into natural log 1 plus 0.5 by 1 minus 0.5. Okay, so this will be the off time. So it will be twice that on time. Okay. Okay, so let me show the solution. Oh sure, like for example, if here it is plus Vsat. Okay. Okay, so what will the voltage here with respect to ground? It will be plus. Okay, so initially we will assume like there is no current, right? Initially there was no current here also, here also. Okay, so when this is high with respect to ground, this diode D1 will be on, right? So this is connected through this path. Okay, so when this diode D1, I am giving a voltage like this will be on. Okay, okay, so that's it, like D1 is on. Similarly here if I consider like I will do one thing. Okay, so So this is connected, right? This is connected means what is the voltage here? Same voltage as here. Like see, since whenever D1 is off, both D1 and D2 off, whatever is the voltage here, that is the voltage here. So the current is 0. Okay. So what is the voltage here? That voltage is this voltage across this capacitor. Okay. So suppose like initially the capacitor is 0, like capacitor is discharged. So what will be here? So this voltage is similar to this ground. So this is D1 is on. Hello? 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 Yeah. So like for example, this is 10 volt, right? So this is 10 volt. Now the capacitor will charge, right? So now the D1 is on, right? Now D1 is on, D2 off. Okay. Now the capacitor will start charging like this. Okay. So this voltage will rise now. It will rise from 0 to it will increase till a particular voltage which is comparable here. So what is the voltage here? V0 by 2, right? So it will be 5 volt. So till 5 it will increase. So till 5 it will increase like this from 0. Okay. Till 5 it will increase means again what is the voltage across diode? It will be again the same, right? Definitely it will be, say diode, if diode is mentioned as which one, like only at like initially. So I will draw here. Yeah, this is 5 volt. Okay. So capacitor I didn't took directly. I mentioned like whenever initially if it is 10 volt, this diode D1 is on, right? So initially I assume like the capacitor is discharged, there is no capacitance voltage across it. So this is 0 volt. And what is the voltage here? This voltage and this voltage same. So it is like in effect it is like this is connected to ground, right? Initially assuming that capacitor is discharged or there is no voltage across the capacitor. Okay. So at that point D1 will switch on. So D1 is switched on like this. Okay. Now since it's switched on, the capacitor will start charging slowly like this. Okay. The capacitor will means charging like this. Say like it's charged to 1 volt, 2 volt, etc. and till 5 volt it charge. Yeah. Okay. So at 5 volt, that's what I mentioned here. At 5 volt, again the output will go to -10. So now it is again like here it is 5, here it is -10. It will be reverse like that, and D2 will be on now. Okay. So that's how we find D1 and D2, or not D1 and D2, T1 and T2. So on substituting that, we will get the T on as 0.242 millisecond and T off as 0.483 millisecond. Okay. So now coming to the 10th question. So for a monostable multivibrator shown in the figure, find R3 which results in 1 millisecond output. Pulse for capacitance C equal to 0.1 microfarad, beta equal to 0.5, Vd equal to 0.7, L1 and minus L1 as 10 volt. Okay. So again this is the same monostable multivibrator. So we know already we know what is the on time, right? So the voltages is given, all the values are given, right? Also what is the required time period is also given. So we just need to substitute the time period and all those given values. We can directly find R3, right? So we can say like what is the output pulse on time of the multivibrator T equal to R3 into C into L minus whatever this peak, since the output changes like this. Output changes like this. What is the peak minus L minus voltage? Okay, that is here. So L minus plus Vd by L minus into 1 minus beta. So this is the time period of a monostable multivibrator. So this is given, L minus is given, Vd is given, beta is given, L minus capacitance is given, and T also given as 1 millisecond. So we just need to find what is R3. Just rearrange and substitute the value. We'll get it as 13.143 kilo. Okay. So again, it's a straightforward question. So I guess that's all for today. Yeah. Huh. Yeah. Okay, I will do one thing. I will just take a page. So like actually it is when we see that I remember that, like, see. Okay, this one. So whenever AF is A by 1 plus A beta, so this is from what I find. So sir also has mentioned, right? So whenever like e power j theta, so like when theta is 180, right, 180 degree, A by 1 minus A beta. Okay, so it is like positive feedback now. So whenever sir has mentioned, like when A beta is less than 1, it is stable, and A beta equal to 1, it is is unstable, or it is like oscillatory, right? And also for A beta greater than 1, it is unstable. The question was like when A beta is greater than 1, definitely it is like A by some minus 9, something like that value will come. So definitely AF will be less, right? So that was a question. So it actually should have been stable. So sir also mentioned as a statement, like though it seems to be stable, actually it is unstable. So for that we have to check how, if for example if an error signal comes into that, how that will affect the output. So we'll see, like suppose there is some error signal here. So here input, and there is some feedback signal input here. So error will be definitely equal to Vi minus Vf. Okay. So why this is unstable is like, even if there is no signal, input signal here. So suppose Vi is 0. So suppose Vi is 0, there will be definitely error signal, right? It will be minus Vf. Okay. So like this error, if I pass through this loop gain, so what will be Vf now? New Vf dash will be equal to this error. Say I will consider it as error. So E. So E into A beta. Okay. So Vf dash is A beta into E. A beta into E. So whenever there is some noise here, say some noise, like definitely whenever we like not ideal, like in practically whenever we implement a circuit and we give some bias signal, definitely there will be some noise floor. Okay, so that will definitely create an error signal here. It may be very low, like for example it will be 1 millivolt or some microvolt and all, but that into A beta. So like if A beta is greater than 1, in each loop this Vf will increase. In each loop this Vf will increase. So in previous loop, say for example if previous was T1th time, this will be less than the next time period signal T2. Like for example at T1 time I got here it as error as E. At next time period T, it will be greater, like A beta into E. So as we see like that, at steady state or time very high, when the time increases, this error signal will go on increasing. Okay, so error signal will go on increasing. So there will be definitely a signal coming like this. Okay, so it may start from some millivolt, so gradually it will increase and it will go to infinity. So that's why it is this system is unstable. So that's why it is actually an unstable system. Okay, that's the reason. So, but when we check here, it won't be. We can't understand. When means it is. We can assume it is stable, but in practical case, it is unstable. That's why. While designing an oscillator, always actually we should have set a beta equal to 1, right? But usually, when designing, we'll try to keep a beta greater than 1. So, definitely this is an unstable system. Other thing is like there may be some like even though it is a beta, due to some due to the components values, it can reach to even if I have designed for 1.1, it may go to 1, means the value may reduce. So that like due to some error in the or the tolerance of the components used. Okay, so always while designing the circuit, we'll try to keep it greater than 1, a beta greater than 1. Okay, so it will be unstable, but due to the error, it will be near to 1, so we will get a sustained oscillation there. That's why. Okay, so I assume that is the reason why we say like when mode a beta is greater than 1, it is unstable. Okay, I think it's clear. Okay. 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 Which one? Vein bridge. Okay. I will draw a block diagram here. Okay. So we took a positive feedback system. Okay. Okay, now okay, beta of s, yeah, correct. Okay. Correct. Okay. Correct. Correct. How angle must vary so that to get stable oscillation. Okay. Actually, I didn't went through that class, so can you elaborate that? Like for example, I will just mention like a beta j omega. Okay. Now it. Okay, sure. So x. Okay. Wait. Okay. Y is theta. Okay. So like for example like this. Okay. Okay. So like perturbation, right? Somewhat like this. Okay. Perturbation means like please. Okay. Means perpendicular to omega. Okay. So okay. Okay. like I guess like for a particular frequency, uh, like the perturbation is like there is a shift, right? There is a shift in this value. Okay, shift in theta. So like the what is the frequency at which a particular, like I will take under color. Okay, so like say my theta here, this is 360. Okay, so if I check here without perturbation, this is the frequency at which I will get the oscillation, right? While with perturbation, this is the value at which I will get the oscillation, like omega naught dash. So definitely there is a change in the frequency. Definitely there is a change in the frequency when how this perturbation occurs. There will be some tolerances in the component selected, right? So like if I selected 200 ohm, you will be connecting some 201 ohm, so there will be small change, variation in the omega naught, right? Similarly, if I take here the perturbation is like the value, the change in theta, right? But theta is like hello, yeah, at the same frequency, what is the change in the value? So but the theta is fixed for a frequency omega naught. Okay, right, theta, like not theta is fixed, like frequency is fixed omega naught. So at this frequency we'll get the 360 degree. So even if there is any perturbations, it won't affect here. There is no shift, right? There is no shift. Yeah, theta is varying, but at this frequency we have 360 also, right? This is also there. We have other phases, correct, but we have 360 also, right? Rest all won't affect, right? Rest all will be degraded, like means deteriorated. The signal will be deteriorated, but only the component at which the theta is 360, that only will sustain oscillation. So we will get output. Other compounds, definitely it will be there, it will return to 0, right? Like even though all the how these perturbations occur? Tolerances. So like say, let me assume, like I don't know, I have not checked till now, I will check, say omega by some k. Okay, so there is some change in this k value, right? So this k will change the angle theta. So if the slope with respect to frequency, right, with respect to frequency, if it is like this, in this case definitely it will shift. Okay, so for each frequency, but I don't know how this is being done. Let me check, like for example, if theta angle A beta, right? Maybe theta is some, but it changes with frequency. So I don't know how sir has done this, but I'll check with this. But sir is mentioning like with respect to omega, if the slope is like this. So 90 means how he used to mention that. So it is like 1 by s, right? 1 by s. For each frequency it will be 90. So it will be T. Okay, I don't know how this is being mentioned. So as I mentioned, I have not gone through this the class. I will check it. Okay, and in a similar way I have explained today today's class. So we had a confusion last week, right? Similarly, I will think of it and I will explain to you why how this is being drawn and how the perturbation don't affect here. Okay, If this is the case, I don't think that perturbations will affect, but still I will check and tell you correctly. Okay. Okay. Thank you. Hello. Yeah, sure. Yes, you are audible. Oh, okay. Uh, huh, huh. Uh, like bistable, like I guess you're confused with like I will draw two type of bistable multivibrator. Bistable multivibrator, actually the multivibrator used bistable multivibrator used or realized using the op-amp is actually Schmidt trigger. Okay, it is actually the circuit is known as Schmidt trigger. So I will draw two circuit. Both the circuit we have explained today. This is one circuit. So R1, R2, and we are giving some input Vin, and another circuit is like so here it is grounded and here is Vin. Okay, so these are the two circuits. Like multivibrator means like the output actually the output varies. Like see, it is actually an oscillator, but in oscillator when we saw like sinusoidal oscillators and all, it varies, like the signal output is continuous, right? But in multivibrator the output is like it's actually fixed, right? Like for a particular time it is some voltage 5 volt. After that it will vary to minus 5 volt, something like that. So it has only two state. The output is some square wave. Okay, so like if the output continuously changing like this, like from plus 5 to minus 5, it continuously change without any intervention. So the output is not actually stable. Like the output actually varies from time to time. It varies. So it is known as so it has unstable state. So how many stable or in multivibrators we assume only two states, like one stable state and one unstable state. Okay, so if the output varies continuously like this, it has like we have two stages, like plus 5 and minus 5. So for both the cases it is unstable. So both the two stages are unstable. Okay, so that's why it is known as astable multivibrator. That is, there is no stable state. So that is known as astable multivibrator. Okay, and if for somehow I created one circuit for which it has one stable state, one unstable state. That is like I gave some input to that. Okay, I gave some input, and due to that input it suddenly changed from its unstable condition, and slowly after a time it goes back to its stable state. For example, if it was already stable, okay, it was at some plus 5 volt, at some input like some trigger or some disturbance which we created manually, it will suddenly go to unstable condition, and this is the unstable, and after a while it will go back again to stable. So it won't be affected later. So again it requires that this is monostable, that is it has only one stable case, and this is unstable condition. Okay, and for bistable always it is stable. Like if I manually made to some plus 5, it will stay in plus 5, unless otherwise I have given some input again to make it minus 5. So based upon our trigger, whether I need to give some input such that the output goes to plus 5 or minus 5. If it is plus 5, it will stay in plus 5 until when we just give some input to that. So that is bistable. So whichever state you put, that will be stable in that in that state. That's it. So that is bistable. Okay, so that is multivibrator. In that, a stable multivibrator is considered to be the oscillator. Okay, and bistable multivibrator we used as our flip-flops. It's similar to a flip-flop. So if I give 1 to it, it will store 1. If I give 0, it will store 0. You understood? Yeah. Okay. V equal to A V1 by minus V2. Okay. Correct. This one, R1 and R2. Yeah. Okay. Oh, let me check. I don't know. Yeah, I understood. Like, but I don't know why. But I'll check. Like, if I write. Okay. Okay, I will do one thing. I'll just try to get that video, right? That's good. Apparently we can check. I don't remember, means I would have gone through earlier. No, I will just log in and I'll check. Maybe in multivibrators, right? Okay. I will try. I will switch off the audio. Okay. What is the timestamp? Oh, not to L20, right? Okay. This one. Okay. This A into V1 minus V2. Okay. Yeah. Okay, I'll show you. So, I understood. So, like, okay. So, actually, this is our amplifier, right? Plus minus. This is our normal op amp. Okay, so I have some input V1 and V2 to here. Okay, so what is the output here? Actually, it is A into V1 minus V2. That I know. So suppose say like V1 and V2, if V1 and V2 is same, it will be 0. But say some V1 minus V2 is some value, so I will call it as some delta V, some small value, 2 millivolt or 20 millivolt, we don't know. So what will the gain here? A into 20 millivolt. Okay, and since there is no feedback here, and gain of normally the op amp will be in power like 10 power 5, 10 power 7 and all. So definitely this will be very high. So for example, if it 10 power 5, what will be the value? 2 into 10 power minus, so 10 square, like 2000. So output must be 2000 volt. But it won't go to 2000. The output will be saturated. Like instead of there will be a limit, right? After that it will be saturated. So output will be saturated. Similarly, if it is minus delta V, it will be minus 2000. So that is, it will be again saturated. So I think sir mentioned that the output when it is in this feedback or means in this format or in while considering the bistable multivibrator, the output will be it acts as an like it is somewhat comparable with the comparator circuit, right? So it is it is similar to comparator circuit, and output either goes to very high, say plus 2000 or minus 2000, or plus VSAT or minus VSAT. Volt to 2000, it will be VSAT, like 15 volt, minus 15 volt, and not, it will saturate. So we have to consider. Yeah. Huh. No, this is like, just check to which node we have connected. This minus and plus, right? Only when I connect a feedback to the inverting node, okay, then only our virtual ground concept will work, or the feedback method will work. Otherwise, if it is non-inverting, we cannot assume that. Like, this is actually similar to our positive feedback, right? So it will add on, and the output voltage will rise up. In negative feedback, the output is like it will slowly it will reduce, and it will go to a stable state. So when definitely not virtual, I mean the feedback method that we have assumed, like R2 by R1, the gain we can consider it as minus R2 by R1 only when if it is connected to this inverting terminal. But if I connected feedback in non-inverting, we cannot use that, because that is in positive feedback, and in positive feedback the output will it is actually unstable, right? The output will rise slowly, and it will go to saturation voltage. So there we cannot use or we cannot assume the same gain that we found for negative feedback. Huh. Correct. Okay. Yeah. Okay, sure. Okay. Okay. So let me. I didn't get you. Like. Yes. Like this one, right? In loop condition, okay. Okay, I don't know, means I have not gone through that. Okay, like usually if I want to design it, I guess you can take what is the on resistance and off resistance there. When it is off resistance, right? Diode is on. Diode on means breakdown region means off, right? Okay. Then I understood. Yeah. Okay. So what is the breakdown resistance given there? So you can assume that, right? RZ. No, definitely there will be resistance there, RZ value. We cannot consider it as net. Yeah. Sure. Like I have not. I have not gone through that. I don't know whether. I'll just check. It's fine. Which one? Okay. Okay. Which time span I can? I'll check. No, how, like here it is like V set naught plus I set R set, right? This we here substituted that. That's it. Like so I have okay. Anyway, I'll check. So V naught is V set plus I set R set, right? So he has just substituted that, like minus V naught, right? So minus of this one, minus of this term. No, I will show you. I will show you here. So, oh, I have to replace this. Okay, so see, like so that V naught was equal to V z naught plus I z R z, right? So if I substitute here, I will be equal to this was the voltage, right? V z naught plus I2 R z. Oh, I didn't check that. Let me check. That I didn't check. Okay, I understood. Oh, the current is flowing in this direction. So plus no. See. Okay, I will do one thing. I will take the screenshot of this also. So let me check. Take a new. Okay, so here so when the current flows in this direction, here it will be plus minus voltage, right? V R Z will say, and this is diode, right? Zener diode. So here already it is plus minus, right? So it was like Zener diode. Okay, a current I Z flowing like this. So plus minus. So the net voltage across is V Z plus I Z R Z. Okay, now I think you can link, right? Okay. Okay, sure. Okay. So I'll be online till 9. If you have any doubt, you may please just mention that. Okay. Yeah, hello, hello. Please. Okay, okay, okay. Sure, sure. Okay, okay, let's check. At what is the time? Yeah, yeah, I think I switched it. Okay, okay. Oh, I think I will again open it. It's fine. Huh? This one, right? This one. Uh-huh. Uh-huh. Yeah. Mm. Okay, let me check that circuit. Okay, anyway, I'm just bringing that circuit. Okay, I think okay, so actually this is equivalent with respect to the V not 1, right? Huh? I think that is the reason he has assumed this output V not to be at ground. Okay, so here I'll just check. Okay, so that is so. Okay. Okay, so like he has already given like found out the current through that, right? So he has not shown that. I guess. Let's check what is the current. Correct, correct. Huh. I'll show you. What is the current flowing. We'll check. Negative resistance to this input, right? So okay. I'll just take another state. So with respect to this input, right? With respect to this input, he has considered, right? RF. With respect to this input, RF is negative, right? So like if I have applied one voltage here, the current should have been gone in this direction, right? But the current is here 2V minus V by RF. So it is just reverse, or V minus 2V by RF means it is minus V by RF. So it's like it is like a negative resistance. And I think sir has drawn that equivalent based on this input V01. So in that case he has assumed this to be grounded. Okay, I think so. I think so. What is the thing? Okay, okay, okay. Yeah, sure, sure. I'll check the circuit. I don't remember. Means I have gone it earlier, but I'll check. I'll check. Okay. It is similar to WinGrid itself, right? So check. So again here, so as we can see here, this is that forward gain, right? A, and this output is given to this signal. So this is actually the feedback. This acts as a feedback. Okay. This acts as a feedback. Okay. So I think some frequency, at some frequency, these components will provide 360-degree phase shift here. Since here itself, this is actually non-inverting amplifier, and this entire will create a 360-degree phase shift. 90-degree with respect to this, right? This point and this point is 90. It doesn't mean this point and this point. Okay. So mentioning like sir mentioned like here, if there is a sine wave, you will get a cosine wave there here. 90-degree phase shift it is. But in effect, if I check entirely, there will be 360. Otherwise, it won't oscillate, right? That I have to check. Correct. Here 180 is there from this point to this point. Okay, I'll check. Okay. Yeah, here. Okay. Oh. Okay. I think it is on resistance he mentioned. This is actually equivalent for the diode, right? Yeah. So it is DC resistance. Okay. Anyway, AC or DC? I don't know. Like this is actually that piecewise linear model, right? So I have VD versus ID curve of diode. So if I assume it will be somewhat like this. At some video it will change this. At some video this is a new voltage, and from there the current will rise slowly. When it's not slowly, abruptly it will change with voltage of diode. So this, what is a resistance? So at each point there will be static resistance, right? So in effect we'll say this slope is actually the resistance of that. So that is taken as dynamic resistance, or we will assume it as AC resistance. So delta VD by delta ID. So that is that resistance. So based on this resistance only we will model. So this is, so say this is our non-ideal op-amp. So here we will model this non-ideal op-amp like this. So this is ideal op-amp, not ideal op-amp, sorry, ideal diode. So we have a source here. So what is source here? VDO, but it will be new voltage here, plus minus, and a resistance here. So what is the resistance here? We'll assume we'll mention this RA. RA means delta VD by delta ID. So this is the actual correct. So this is the piecewise linear model for that. Okay. So any other questions? Yeah. Yes. Okay. Average. I didn't understand about average current. It is like bias current, right? Bias current. Correct. IB minus, correct. So like this is the average value. So it is known as I average, right? And offset means what is the difference between the between these two? That is offset. Offset between the bias current. Like it will be given. Like if they will specifically mention what is IB minus and IB plus. Okay, I don't think they will give like if they are giving I average and I offset, means we have to determine IB minus and IB plus right from here. Otherwise, like if I want to like find what is the result due to this non-ideality, what is the change in output voltage due to this non-ideality, we must know IB minus and IB plus, right? So like if I have a inverting configuration like this, I have grounded this, P in means definitely I need to know, since only the effect of IB minus is having the effect here. So like we not, so the current here, if it is I1, this current will be I1 minus this IB1, IB minus. Okay, in another case I will show you where IB plus will come. So minus plus. Okay, so I have a resistance here, say R3, say R1, R2. So IB minus and IB plus, like this. So what is the voltage drop here? So current is flowing like this, so plus minus. So the voltage at this point is not ground here now, it is not equal to 0. Now voltage is minus IB plus into R3. So we have to assume this. So this is the voltage here. So V minus this voltage by R1. So that all those things we have to consider that. So we have to understand what is IB minus and IB plus. Means previous questions, the main exam question, right? I don't know, means we don't have access to that. I think you can mail to NPTEL mentioning this, they may help. Okay. I think it will be if you solve almost all the assignment questions, I think you will be able to crack that. I guess. Means, I feel. Yeah. Hello. For what? As mentioned, like like all the questions that we have done today, or a new question? Definitely. Like all these each I used to upload, so I'll just share you that. So I think you can see here at the end, like at the page at the end, there is problem solving section, right? So you click that, you go to problem solving section. There like not only mine, like in this spreadsheet you will get that. So week 7, like I have not uploaded, I will upload it today or tomorrow. So there are two more TAs, you can get theirs also. So you will get consolidated many questions, right? So see, till sixth week I have uploaded. Yeah. Okay. Also this video will also be available. Okay. So by tomorrow I will upload, so you can get that also. Okay. So I think it's already 9. So if there is no other questions, I guess we can stop, right? Adityan and Pradeep, we can stop today. So thank you all. So we'll meet next week. I think next week will be last week, week 8, right? So we'll meet to next week. I will upload this video that I have recorded now by tomorrow morning or tomorrow afternoon, and also the PPT in that folder. Okay, so see you soon. See you next week. Good night all. Bye.